Hello, ladies and gentlemen. Today we're going to be talking about translation, going from our mRNA to our protein, the end of central dogma. This is done outside of the nucleus in the cytoplasm. Now we talk about the other types of RNA. rRNA, or ribosomal RNA, has two subunits, the large and the small. They come together to create the 70S ribosome. And this is the site of actual protein creation. The tRNA not only looks like a T, but it's also known as the transfer RNA because it transfers or brings in amino acids from the cytoplasm to build our polypeptide chain or our protein. The tRNA has an T codon on this. Let me say that again. The tRNA has the T codon. An T codon is the complement to the codon on the mRNA. Take a closer look. So our codons in the mRNA are here. On our tRNAs, we have complementary or matching T codons. Again, T codons are on the tRNA. And each of these tRNAs brings in a specific amino acid. Translation is the process of reading the codons in the mRNA and creating an amino acid sequence of our protein. Our key players, we have the initiation factors that start the whole process. Our ribosomal subunits, both large and small. We have our mRNA that has the codons that are the instructions on how to build the protein. We have our tRNAs with our T codons that bring in the building blocks of our protein. These building blocks are the amino acids. And finally, we have the release factors that bind to a stop codon and terminate this whole translation and releases everything, and then it can move on. So, initiation. Initiation factors 1, 2, and 3 bind to the mRNA and bind the small subunit to the start codon. Next, a tRNA comes in and brings in the starting amino acid, which is methionine. Finally, the 50S subunit fits over and creates the 70S ribosome that has three main spots, an A site, a P site, and an E site. During elongation, new tRNAs bring in amino acids and enter the A site, or the acceptor site. The ribosome will shift down, and this tRNA will move into the P site, where the amino acid will form a peptide bond. So the P site has peptide bonds, and connect it to the protein. Once the ribosome shifts down again, the empty tRNA will be in the E site, or the exit site, and it will leave to find another amino acid in the cytoplasm. For termination, a stop codon is reached in the A site, the acceptor site, except there's no tRNA that matches it. So the release factor comes in and binds to that stop codon, and the whole thing falls apart, releasing that protein to be folded into a functional shape or conformation. One mRNA strand can have many ribosomes on it at the same time, creating many copies of the protein. The genetic code is universal. Every living thing has this type of genetic code. It's read in triplets in codons, and one triplet encodes for one amino acid. These codons are not overlapping. You read 3 and then you read the next 3. So we have between 20 and 22 amino acids. And the genetic code is known as degenerate because there are some codons that encode for the same amino acid. Now, that means you can't go backwards. So let's take a look at this. Again, with the set of 3 triplets, we have 64 different options. 1 start codon, 3 stop codons, and then we have 60 left to encode for 22 amino acids. So we have a lot that encode for the same amino acid. So if we're looking at our protein and we see a specific amino acid, we can't go backwards. It's degenerate because we do not know which codon encoded for that amino acid. we could have several that could encode for that amino acid. Protein folding. After synthesis, the protein must fold into its three-dimensional shape or conformation. If it's misfolded, the protein is tagged and dismantled, hopefully. Proteins can be folded in more than one way. A misfolded or denatured protein can cause disease because it is less likely to perform its function. Temperature is the number one thing that causes a protein to denature or unfold. Well, that's right, Four Eyes. You're nothing without me. While I'm essential for any protein, even yours, you're still a so-so professor with no chance of tenure. Well, your amino acid